Hi again. As we discussed in the last video, the idea of vorticity and the generation of vorticity at a rigid wall or boundary had to do something with the notion that we have the no-slip condition in a real flow. And when we discussed potential flows, we noticed that the caveat that we had, or the drawback that we had, was the fact that we ignored the viscous terms, which are the second order derivative usually. And because of that, our equation turned into a first order equation. And then we couldn't really have all the boundary conditions that we had for full Navier-Stokes equation. And the boundary condition that we got rid of was the no-slip boundary condition. But in reality, the no-slip boundary condition is important. Fluid elements, when they, for example, you have a uniform flow from infinity coming and approaching a flat plate that starts from this point, fluid elements very close to this wall, to this geometry, to this flat plate, they will have exactly a velocity equal to 0. That's the no-slip boundary condition. A little bit above it, they also have a velocity that is non-zero and is finite, but is very small. So you can think of a region very, very close to this wall where fluid elements are almost stationary, or almost having extremely small velocities. And if you calculate a local Reynolds number there, and you can think of Reynolds number as a ratio of inertia, local inertia of fluid elements over the local viscous stresses that fluid elements feel. If you take this ratio and call it a local Reynolds number or Reynolds sublocal, for those points, for those fluid elements, it's as if it's almost 0. So you can think of that those fluid elements probably feel a flow very close to the wall that is very much like a Stokes flow or lubrication flow. It's completely dominated by the presence of viscous stresses. At the same time, we know that very far from the geometry, extremely far from the geometry, fluid elements will not at all feel the presence of the wall, or will feel very little of that presence. So what you have is viscous stresses, and anything related to viscous deformations will be negligible there. And if you take the ratio of inertia over viscous stresses for those points very far from the plate and construct a local Reynolds number, that local Reynolds number will be actually much larger than 1. For example, for the flight of an airplane, if you take fluid elements way above the wing, their local Reynolds number can be order of 100,000 or something like that, a very large ratio. So there is clearly a transition from a region that is having 0 Reynolds to a region that Reynolds is much larger than 1. And maybe we can separate the flow with the idea of a boundary layer into 2 regions. A region within which the local Reynolds number is of order 1, or order 1 going to 0, and a region outside it when local Reynolds number is definitely much larger than order 1. This boundary layer is a mathematical way of dividing our problem into 2 regions and dealing with each region in the according manner that will be based on certain approximate version of Navier-Stokes equation. In this outer region, we said that viscous stresses probably are negligible, so we can solve the flow using potential flow. In this inner region, we have a different scenario. We cannot really ignore viscous stresses anymore inside the boundary layer. At the same time, we cannot ignore the inertia. They are both important because their ratio is of order 1. And that's what gave us or brought us into the boundary layer approximation of Navier-Stokes equation. For a 2D flow, we found that the x component and the y component can be approximated in this manner, that in the x component, we have the convective terms for acceleration of fluid elements. Since the problem is a steady state, we don't have the transient acceleration. We only have the convective acceleration. And on the right-hand side, we have the pressure gradient and the dominant viscous term, which is the second derivative of Vx with respect to y. Why we are not keeping the d2 Vx over dx2 is because of the fact that the length scale in the y-axis, over which velocity will feel a certain change, is much, much smaller, that's the thickness of this boundary layer, than the length scale over the x-axis, which is the length of the plate L. So this underlying assumption that the delta or the thickness of this boundary layer is much smaller than the length of the plate is what helps us to keep only this term for viscous stresses and ignore the other viscous stress or viscous component here. The y component of Navier-Stokes similarly can be simplified, and we notice that it only gives us that pressure gradient normal to the plate inside the boundary layer is negligible. This is when we neglect variations due to hydrostatic. But if we want to keep them, as we have shown before, you can always construct a modified pressure, which is P plus rho g y, and then you can rewrite everything in terms of that modified pressure, and you will get exactly similar forms at the end of the day. Now, what really this equation tells us is the fact that if pressure inside boundary layer at a fixed x vertically with y is not changing, in other words, pressure in the boundary layer, inside the boundary layer, will be set by the pressure distribution outside the boundary layer as a function of x. And this fact that pressure inside the boundary layer is imposed by the outer flow is how the solution from the outer flow speaks or communicates with the solution inside the boundary layer. And at the end of the day, our problem comes down to solving these two different regions together and making sure that they are talking with each other or communicating with each other through the pressure. And the fact that the pressure field inside the boundary layer is set by the pressure field in the outer flow enables us to do that. Let's think about, before doing any calculations or any algebra or math, and as you have seen, this is not really easy. Blasius solution requires some numerical integration. Before doing that, let's just think about the order or the scale of different terms that we have. If you think about the left-hand side of x component for Navier-Stokes and think about a scaling of these terms, you can easily see that the left-hand side scales as rho multiplied to a certain velocity squared divided by a certain length scale, which let's say the length scale of the plate goes as L. Similarly, if viscous stresses are in balance with inertia inside the boundary layer, then the scale of viscous terms should go the same as inertia, and viscous terms scale as mu times the scale for velocity, which is again u0. And u0, if you want to remember, is the velocity of the free stream that is coming over the plate. Mu times u0 is a scale for viscosity divided by a length scale squared, and that length scale here is the thickness of the boundary layer at a position L. So delta at a position L squared. If we follow this scaling, this tells us that delta at position L scales as square root of nu, which is kinematic viscosity, multiplied to u0 divided by L. So again, if you have forgotten, kinematic viscosity or nu is the dynamic viscosity or mu divided by density, which is rho. We could also take L out and write this scaling for a general position x. So delta at a position x along the plate is scaling as a square root of nu multiplied to x divided by, and I think I'm making a mistake here. So one thing that I need to correct here, this should be, so the mistake that I made, and I'm correcting it here, the u0 comes out here. This would be L here, and the u0 goes in the denominator here. And how I notice this mistake is because of the fact that nu should be multiplied to something that has dimension time. So length divided by u0 will give me time. That's the mistake that I did in the algebra there. So to correct it, it will be nu multiplied to length divided by u0, which is velocity, and the square root of that. Length is meter, u0 is meter over second. Meter divided by meter over second gives me second. The scale or dimension for kinematic viscosity is area per second. Area per second multiplied to second will be area. A square root of that will give me meter. And the same thing here. I can replace L with x, so I get delta as a function of x goes as a square root of nu x over u0. And you can simplify this, make it dimensionless. Delta as a function of x divided by x will go as 1 divided by a square root of Reynolds. And let's actually do that. Yes, the square root of Reynolds based on x. So that's how we find the scalings in this phenomenon. So the most important thing to keep in mind is the fact that we didn't do any solution, we didn't do any numerical integration. Just by scaling, we reached the conclusion that indeed, if we want to divide our problem into a region where viscous stresses are having the same scale as inertia, and a region where inertia terms are much larger than viscous stresses, the dividing line should actually be increasing with the x component, and it should increase with the x component in this manner that it goes as a square root of nu times x over u0. And this is, again, you can go and watch the other videos. This is very much equivalent to what we had in Rayleigh problem, where delta is scaled as square root of nu times t for a transient motion of a flat plate that was stationary at time 0, and all of a sudden at t0 plus and epsilon after 0, we started moving it with a constant velocity. This is exactly the same idea in boundary layer, and the thickness, which is the length scale for diffusion of momentum or vorticity, increases in a transient problem with time. In a steady problem, it increases in a convective manner with x, and it goes as a square root of nu x over u0. Now, we notice that may give us an idea about how this delta 0.99, where velocity reaches to its 99% value, scales with x. So it's going to go as the square root of nu x over u0. But really, this idea couldn't bring us any further, because as you have seen in many of these scaling problems, the numerical prefactor is unknown. We can find the form of the solution that is correct, but the numerical prefactor is unknown. And to find that, one way is to go and do the numerical integration through the Blasius solution, find the self-similarity parameter, self-similarity equation, and solve it numerically, which is relatively tedious and time-taking. Or we can actually try to solve or approach this problem using integral methods. And that was the idea behind von Karman-Polhausen integral method, which we will review in the next video.